Hello, everyone, and welcome to today's seminar. Can you just give us a couple of more minutes? We're waiting for a few more attendees to join, so we'll be starting the seminar in a couple of minutes more. Thank you. Okay, welcome to today's webinar, which is the second in a series of webinars that we plan to roll out, covering various topics relevant to antenna technology in real-world business applications. My name is Gordon Petrie, responsible for sales and business development at Antennaware, and I have the pleasure of introducing today's topic, which is exploring antenna impact for robust wireless asset tracking and monitoring. Today, I'm joined by Dr. Gareth Conway, CEO and co-founder of Antennaware. It's nice to see some old faces joining us today. And for those less familiar with Antennaware, we are a deep tech company commercializing disruptive antenna technology that solves wireless connectivity problems in market sectors, including sports, audio, industrial IoT, and healthcare. Our aim is to offer this technology to companies that are developing wireless products for challenging platforms, primarily wearables, but also other IoT platforms. Antennaware was spun out of Queen's University Belfast in 2020, and our antenna technology is patent protected across all frequencies. Now, before I hand over to Gareth, there are a couple of housekeeping points. We reckon the presentation will last approximately 35 minutes, and then there'll be a Q&A session of around 10 to 15 minutes at the end. You'll see a Q&A icon facility at the bottom of your screen, so please post questions at any time during the presentation, and we'll try to answer as many of those as possible at the end of the day. So, without further ado, Gareth, please take us away.
Thanks, Gordon. So we created this webinar to address some of the applications that we see around industrial tracking and monitoring. So from real-time location tracking, safety and security monitoring, and tracking within smart factories and reading from sensors, and to address some of the industrial 4.0 applications. We've created three topics within this webinar. Topic one being asset and personnel tracking in industrial environments. And from this, we want to dive into the understanding of the common challenges. And the outcome that we hope the people on this webinar will gain is a better understanding of the wireless communications in challenging environments. Topic two within the webinar is on antenna solutions that address these common challenges. We will offer some tips on antenna selection for difficult platforms, including on and near the human body or on metal. Topic three looks into antenna performance comparisons with performance gains in real-world applications. So really the outcome here that we're looking to achieve is what good looks like in real-world applications for our engineers tackling these problems. So let's dive into topic one with an understanding of the common challenges. Before I dive into this, we want to sort of set the scope that we're interested in. So we're talking about tracking assets and platforms, looking for data transmission of these or positioning those platforms will be in industrial environments, the human body, it could be on forklifts, and it could be on anything metal. The application operation environments will span anywhere from low anechoic environments to highly multipath environments, so where you're in around a lot of metal structures or in a densely populated factory. So on that there, to define the difficult platforms, we see difficult platforms in terms of wireless communication, anything that is conductive or has a relatively high conductivity. So as we move up in frequency, human tissue with a high water content and salt, there is a conductive difficult platform, and also obvious solutions like any sort of metal. In terms of the scope for wireless system considerations, we're interested in maximizing or optimizing the received signal strength to leave us well above a noise floor. And we're also looking at how we achieve reliable performance in congested wireless environments, and that's where the noise floor is unpredictable and can cause reliability issues or data dropouts in marginal links. And also, one of the ones that causes a lot of problems in these congested environments or highly multipath environments is the fading that happens when you try to receive that signal strength and dropouts. So if we first look at wireless trends and we have to decide on which frequency we operate at, a lot of this is firstly decided by your application and the region you're in. But if we look at the global connectivity area, it's largely and densely populated by Bluetooth and Wi-Fi applications, and that's largely due to the interoperability of those protocols that allow people that they can connect seamlessly with mobile phones, and it's one of the reasons why these unlicensed bands are used widely internationally. If we then look at moving away from those congested bands and we're looking to achieve range and widely distributed sensing, for example, in the IoT applications, we're seeing a lot of popularity around the non-cellular 5G standard, where DECT has now become available at 1.9 gigahertz. And also for anything larger range, you tend to drop below 1 gigahertz, where the wavelength is much longer and less prone to blocking and absorption. If we look in then towards tracking and positioning of assets, we tend to see a migration above the Wi-Fi 6 bands into the UWB band for performance quality, where the wavelength is a lot smaller and positioning is better in terms of performance and position and accuracy. If we then pick a frequency and we start to examine or analyze or receive signal strength in these typical environments, we see what looks like a very noisy received signal strength. We've extracted this paper from work by Professor Cotton at the Centre of Wireless Innovation at Queen's University, where many years ago he was looking at the signal fading on difficult platforms like the human body. And the takeaway, I guess, from this is that the signal isn't a constant RSSI, that often to do the analysis, you take an averaged RSSI, which you can work out your link budget. But what we do notice from this is that in a real life signal, it's not just a smooth line, it's fraught with fading, the signal levels going up and down due to multipath. And this can cause a lot of problems for our system designers. If we then do some statistical analysis of that and look at the distribution of fades in a typical time window or typical measurement, we can see that a lot of fades, you get a small minority of fades happening with fades in the order of 25 to 30 dB on the left of that graph. The major fades tend to be in around about 10 to 20 dB, and that happens quite often in a typical link where you have multipath and people moving around in those links. So in terms of the wireless communication, 10 to 20 dB fades are critical and they will cause your link dropouts. What we have to do as a system designer is ensure that our average received signal strength, or the best portion of them fades, do not send us into the noise floor and drop out the link. So what I want to explore in this webinar as a more educational approach is to look at a typical link budget, the concept of link budget, and see where we could offer benefit or what those benefits in terms of dB would mean. So I've sketched a typical link budget here, and the parameters that we're considering in this link budget are TX power, which is generally set by the protocol or the FCC in terms of the band you're operating in. You're going to have a bandwidth on that in terms of the impedance bandwidth. The system that you select, the chipset, is going to have a bottom line receive sensitivity in dBm. You're going to have some noise floor on that receiver where you have to be a port or a significant or a certain dB level above your receive sensitivity in order to detect a clean signal. That is a fairly complex task. You have to start looking at bit error rate, your modulation schemes. But in general cases, 69 dB above that noise floor tends to produce reliable links for low data rate links like we'd expect in industrial IoT applications. What I'm going to look at now is in terms of the link margin. So you have your transmit power here in blue dash line, and at some negative dB level, you're going to have your receive sensitivity. This could be in the order of like minus 90 dBm. Above that receive sensitivity, you'll have your signal to noise ratio or a certain margin to allow a detection level, a clean detection level with low bit error rate. And what we're left with then is a link margin, what we have in terms of link budget for our propagation. If we drew a typical signal like was presented in the research showed previously, where you have not a clean signal, but a lot of fades in that signal, where that blue line intersects the detection level is where you're going to start to see your dropouts, and it's going to be different at different distances, different environments. Usually what we do to have some calculation on this is to take the average received signal strength, and we do this in terms of looking at the detection level, looking where that line or power decays at distance, and where those two lines intersect. On a very simple case, we can say that that would be our typical communication distance. For this example, we'll say it's going to be 50 meters. What I haven't accounted for here is noise floor. And in some early link budget calculations, you may assume that your link is limited by the receive sensitivity and not the noise floor. But in industrial environments, in any environment, that noise floor could be your limiting factor. It could be above the received sensitivity. And if that is the case, then your detection level will have to be a certain have a signal to noise ratio above that noise floor, and ultimately it reduces your communication range. But in fact, that noise floor could be anywhere for any environment. So for the purpose of this example, I'll keep it that we're limited by the received sensitivity, and we have a detection threshold which sets our range. If we could, in that link, if we could add about 6 dB as an example, we could in theory, receive a higher received signal strength, which in fact extends out the point at which we can detect it, and 6 dB would theoretically in free space double our range, and we would extend that out to 100 meters. And I guess the question is, where can I get that extra dB from? So if I take the example where I fix the transmission power, we've maxed that out. The bandwidth is fixed by your system. We're not going to change the chipset. It's going to be the same receive sensitivity. And we have a fixed SNR or detection level above that. We have to then look inside the link margin. And the answer really is in free space with your antennas sitting and nothing near them, your transmitter, power, everything fixed. There's not a lot you can do in terms of your link budget. But on difficult platforms, you have the option where you can look at your antenna efficiency, look on how and optimize how it propagates. And for the rest of this webinar, we can show you some of the gains that could be achieved in that. Ultimately, by improving the efficiency of that link and the propagation, what you're essentially doing is moving the fades above your threshold in order to produce a more reliable link. So you might not want to extend the range to 100 meters, but what you're doing is making a more robust link at 100 meters or at 50 meters. If we look at the problems and what causes the fades in those links, generally when we're line of sight, when the two devices are facing each other, signal level tends to be quite good. It does decay at distance. But the real problems occur when it's a non-line of sight. So when essentially when the two antennas that are doing the communication cannot see each other, they're blocked by an object. In this case, where the research at the Centre of Wireless Innovation was looking at it, and they were looking at the time and looking at the signal as these people turned around, you could see that there was a huge drop in the received power when there was both devices, both systems were in non-line of sight. In this case, it was incredible. Here we're seeing about a 60 dB drop, and that's probably one of the worst cases in an anechoic environment. But it highlights the problem that if you're looking at this, you're going to have to design your experiment or design your test scenario for your system that you're doing the asset tracking for or mounting it on a machine for it to be in the worst case scenario where it could be mounted on the back of a piece of equipment or personnel that's walking around in a safety zone. The theory and the experiments would hold up if we replaced the people with a metal machine or metal piece of equipment that you wanted to track or read data from. So essentially, the problem for difficult platforms is limited wireless coverage. What we're looking to achieve is a more complete coverage solution. On a limited wireless coverage problem, you would get poor radiation efficiency, impedance detuning, and absorption, and that largely depends on the type of platform. So a lot of the early work that we've been doing to develop antennas that are agnostic to the platform, we found that the human body was one of the most difficult platforms, but we'll also show results in this webinar of what happens when you mount it on a very close to a metal platform. So the key metrics that I'm interested in going forward are the radiation efficiency, the impedance detuning when I put it on different types of platforms, and the absorption, so how that antenna radiates and how it performs on typical platforms that we would find in an industrial environment. If we could visualize that problem and we put an antenna or a wireless system on the back of a person to track them, and we could visualize those electromagnetic waves in this cross-section of a torso, we could see that as the electromagnetic waves propagate out from the wireless device and try to go around the body, that there is that blocked shadow zone. And what we're thinking of is maybe a safety monitor on a person, something monitoring the health stats in an industrial environment, or potentially just even reliable comms. There are approaches, and now that we've covered the link budget, you could up the power. If you could do that on your device, you could bring in some circuitry in the front end of that to amplify it. but ultimately you're going to drain the battery much faster. There's going to be cost implications there. You probably, if up the power for, doesn't, not so much on a machine, but certainly on a human, you've got SAR exposure limits, and ultimately it's not the most greenest solution. The other way that you could address the problem of poor coverage and block shadow zone is surround the equipment or the person in a wireless infrastructure, and so that there is no shadow zone, potentially to have a line of sight to each receiver. The problem here is that it's dependent largely on that infrastructure. There's a cost there, and can be a limiting factor in some factories or some use cases where mounting one base station is potentially all that's on offer. When I talk about antennas and propagation, a lot of the theory will explore that far field region on the line of sight. I put this slide up because when we put an antenna on a difficult platform, we're really talking about an antenna that is placed with something quite substantial, like a piece of equipment or the body, in that near field region, in that reactive field region, which means that a lot of this theory, a lot of your free space path loss, etc., will fall over and not stand up when you put something in that Fresnel zone, that near field zone. When we do that, and we look at the performance of antennas in this study, we done 50 test subjects at different frequencies here. The first one, I think, is at 868 megahertz and at 2.5 gigahertz. So in the ISM bands, Bluetooth, etc. We put the antennas under test very close on a harness on a person, and we looked at the return loss. And we looked at the total radiation efficiency. And what you can see, even on just a subset of 50 subjects, that the performance is hugely variable and it's not repeatable or reliable on these platforms. And what we were looking for was an antenna solution that would give us more consistent, repeatable performance so that we could really properly characterize the system and make it more reliable in terms of the communication link. So the antennas we looked at in early studies were never designed for difficult platforms. Some of them might give reasonable performance, where others really, the performance suffers hugely when it's put close to the platform. So in terms of the challenges for antennas and propagation, the number one challenge I've listed here is your resonant frequency detuning, and we've seen that. So it may work well on one piece of equipment or one person, but not on the other. The solution that we're looking for in this is a stable return loss. Number two here is the resonant or the radiation efficiency reduction. So when you put it on a platform, you're going to get bulk power absorption in that platform, in particular if it's conductive. If it's plastic or an insulator, and the efficiency might be fine, but if it was really close to anything conductive, even on the PCB, you're going to get power absorption. So the solution here is to get it to radiate in a way that there's minimal coupling and minimal power absorption in the platform that you're mounting it on. In terms of the platform shadowing, the secret sauce for us was to try and control the propagation from that antenna in order to optimize it to get around the platform and provide that provide better propagation or more optimal propagation in the non-line of sight region. The other challenge is to do all this get like an omnidirectional coverage or wider coverage range. So a lot of solutions to this are directive antennas, like patch antennas, but they don't really have the uniform radiation in order to combat the non-line of sight from being on one side of a platform. You'd have to point it in the right way. The next thing that we look at, and we don't really dive into it a lot in this webinar, is the multipath and fading. And there are solutions, and we have experience of diversity offering significant gains in terms of combating multipath and fading, that being antenna diversity or some sort of channel diversity. The next thing is the receive signal strength, and the obvious answer is to up the TX power and reduce the receive sensitivity in order to provide a better link margin, but they're not always an option for some applications where they're maxing these out. If you're looking to address the size and performance efficiency of that wireless link through the antennas, it really comes down to a question of antenna size versus the frequency or the wavelength you're operating at. So if size isn't a problem, going down in frequency solves a lot of this. But if you're space critical and you need to operate at higher frequencies for positional accuracy or something, it becomes a challenge. So on to topic 2 is where I look at antenna solutions that address these common challenges. So the common challenge is being able to measure these and repeatedly compare the antennas to one another. And we've seen from our research before we started AntennaWare was that consistent and reliable performance on conductive platforms is achieved with antennas that support on-body propagation modes. So the way we looked at this was to put multiple antennas on the same platform and try and maximize that communication across and around the platform. The measurement challenge that we addressed was to test for worst case. So we didn't test our links in line of sight. That wasn't the problem. We wanted to isolate the propagation mode in anechoic environments and compare the antennas where they were most likely to fail on a representative test bed. So many years ago, I got involved in this and we wanted to address the challenge for on-body antennas. We had the concept of what we wanted to achieve. We'd done the analysis through 3D full wave electromagnetic analysis. We wanted to validate that, obviously, so we got volunteers, put wireless nodes on their body and validated the numerical analysis. We then moved into representative test beds. We found quickly through our research that the performance was very much variable depending on who you put it on, and getting somebody to walk in the same way to compare different antennas was quite a challenge. So it led us down a road where we were looking for antennas on difficult platforms and designing repeatable test beds. So to do this, we took the numerical analysis, the full wave body analysis from autonomically correct digital models, and we built a test bed that allowed us to look at not only off-body communication, but around the platform communication. So the test beds we developed for this to get us to a point where we had an antenna that met the design requirements was largely around human tissue. So we built phantoms that were electromagnetically representative of the human tissue morphology, with a skin layer, fat layers, a tank that was made similar to subcutaneous adipose tissue or fat tissue, and we filled it with different liquids, in this case a muscle liquid. We matched them to tissue Gabriel's tissue properties across the frequency range. We're interested in this specifically around 2 to 2.5 gigahertz. And we were confident then within about 10% that we were hitting those properties. And really what's of interest here is that the conductivity of the materials or the platform that was close to the antenna were relatively high in terms of the conductivity. So similar to what you would expect on wet tissue. We used the platform, took antennas that we could find that were available commercially, but also that we were seeing inside wearable products. Some of these from Texas Instruments appear on application notes, and they usually find their way into the very early prototypes of wearable system design or for different platforms. We put it into our reverb chamber at the university, at the Centre of Wireless Innovation. On these platforms, we were able to look at the antenna radiation efficiency. We were able to put it in an anechoic environment, spin it around, look at the radiation characteristics of that platform. We spent a lot of time looking at isolating that worst case scenario where we were getting body blocking. We put it in anechoic environments, minimized our cable radiation, and had a really neat, repeatable setup for looking at anything from sort of about 900 megahertz right through to 10 gigahertz on this setup. The Phantom that's shown here is Popeye 2 from Spig, which runs from 3 to 100 gigahertz. So we were happy that we could isolate the weakest link and do a side-by-side comparison of the different antennas available to see how much or what good looks like in terms of how much gain we could achieve by the right antenna selection in your link budget. So doing a side-by-side comparison, anechoic environment, non-line of sight, we could see that with the various types of antennas, with the right antenna on the top line, we could achieve at least 10 to 20 dB gain in those typical links with the right antenna choice. So in terms of antenna tips in the webinar, I guess the number one tip is don't use antennas that rely on a ground plane to radiate. For example, a small chip antenna where you have to shape the ground plane would, from our analysis, you could see that a high current distribution is on the edge of that ground plane, which will essentially reduce the efficiency when you put it close to a platform. And don't expect antennas to do the radiation. It will be largely from that chip antenna, probably down the side of the ground plane or whatever shape you've cut out to insert the antenna into that in terms of the footprint. And don't design for the best case. So don't be testing it only in that line of sight link. It is important, but really look for where it's your link's gonna fall over or the link's marginal, which generally from our analysis is that non-line of sight when it's shadowed by the equipment you mounted on. And aim to address that problem and test side-by-side tests of antennas that potentially give you the best coverage for your application. So the number one to do is to start with antenna and don't treat it as an afterthought. I've been involved in many projects where they come with an antenna on a board, the case size has been set, and they're looking to really optimize the performance, but unwilling to start with antenna, optimize that first. And if you can get the antenna right, the rest should follow in terms of your wireless performance. Selecting an antenna that's agnostic to the platform you put it on. And that could be the PCB, the tissue, or any sort of metal. And again, test for the worst case, be rigorous and understand its limitations for your application before you send a product out into the market. So my final topic on today's webinar is antenna performance comparison with performance gains in real world applications. So this will walk through the outcome of the research that we've been conducting and what is now available commercially. So in AntennaWare, we have a range of products that span below 1 gigahertz right up through to about 8 to 9 gigahertz. It's the same antenna technology. We call it the body wave antenna, and we look at some of the characteristics of that antenna, which makes it a good antenna for difficult platforms. So what we want to see in terms of the propagation, we take two scenarios here where on the left, we have propagation from a standard off-the-shelf antenna, and on the right, we have antenna propagation from something like the body wave. And you can see that the body wave on the right allows the wave to creep around the surface and cover that shadow zone at the back of the body. So that's a numerical analysis. We have spent a lot of time in chambers looking at really what are the performance gains when we can achieve that type of propagation from an antenna, a low profile antenna, which could be mounted on a difficult platform. We've conducted it on different industry phantoms. We went into the Satamo or Stargate type chambers as well, and we put some volunteers on the right in chairs for about an hour to look at the performance difference between the phantoms and on real people. From that analysis, we've developed and optimized the body wave antennas. So it has the impedance stability, it has omnidirectional radiation pattern, and has consistent radiation efficiency, easily integrated onto a PCB with no sort of cut-out, keep-out regions on the ground plane. And we've provided the rigorous measurement characteristics. So in this application, we were looking at putting it on the torso, and we were looking at the free space efficiency, what the efficiency was like when we put it 5 millimeters from the phantom and 35 millimeters from the phantom. So the impedance stability is excellent at this application, or this frequency range. We're looking at the UWB band, and you can see that it regardless of how close it is to the phantom, it maintains that impedance. So that's one box ticked. When we then look at the radiation efficiency, we're looking at something similar where we could mount it on different types of platforms and have repeatable results. And we're seeing about a 1 to 2 dB at best shift in efficiency. You're going to get some shift in efficiency because it's going to be absorbed as the waves propagate around that platform. And we were happy with the results of this, and we'll have some comparisons with conventional antennas now in a second. When we look at the radiation characteristics, the third requirement that I wish to see, we were looking at an omnidirectional radiation pattern. So if we looked at a printed monopole, you can see a lot of the signal absorption in the pattern from the printed monopole. The body's not completely, or the body wave is not completely immune to any absorption. You're mounting it on quite a large platform, but you can see it's much more omnidirectional. And when we take cross sections of that radiation pattern, we're seeing that about, in some cases where we're getting coverage around the back of the body, you're seeing about 10, in some cases 20 dB difference in the radiation pattern gain. Taking that outside, if this plays for me here, taking that outside, mounting two devices front and back on the body, and looking at the received signal strength when you move around. So this is the received signal strength of a PIFA antenna, I think, in this video, versus, and comparing that to if you selected something like a body wave antenna where you'd have a much higher signal strength. And you can see it here moving with time, taking packets with time. We're seeing that easily seeing that 20 dB in terms of the difference in received signal strength. And this example was using 2.45 gigahertz. If we then move away from the human body, where all the research was conducted in order to develop the antenna technology, and start to look at on-metal challenges. So here we've taken a printed F antenna, which definitely you do see in some of these applications. And one of the challenges is on the left here, we've got it in free space, which is fine, operates brilliantly, efficiency is really high. And you bring it across onto a metal platform, you get a large current distribution, and you get eddy currents, you get a current distribution on that conductive platform, which alters the performance of your PIFA that you'll see in an application note, and it'll really, when it's close to the metal, have a huge effect on terms of the radiation efficiency. If I then take a look at the radiation patterns in free space, the gain pattern, and compare that to when we put it in metal, you can see that there's a lot of absorption in terms of the pattern, or in terms of the radiation pattern on the metal platform, and that's where your performance gain then begins to suffer. This is largely due to three factors. You've got one is a detuning of the antenna on the metal, which you need to account for. So we're looking at the green traces in free space, and when you move it up 5 millimeters from the metal, you get a large detuning and mismatch in terms of impedance. The second thing that you're going to see with that embedded in it is a drop in your radiation efficiency, moving from the green and free space, which is fine, 90% odd, down to the red trace, and that'll be different depending on your match. That'll be different across the frequency range of interest. At this point, we're looking at the Bluetooth band, and then ultimately your total radiation efficiency which includes your mismatch loss, will suffer in some cases maybe 4, and in other cases over 10 dB at parts of the band when you're put close to metal. So looking at a different frequency this time, looking at the DEC band, which has become popular for the sensing and asset data tracking, we can see that with the body wave, when we put it close to metal, again, free space here is in blue, on metals in the orange trace, you do get a slight drop in efficiency. For the band we're interested in is pretty narrow, so we're looking at about 1 dB loss. Whereas if you compare that to a chip antenna mounted on a platform, free space, versus on a sheet of metal, you can see easily that there's about 6 dB alone to play with in terms of the efficiencies, dropped about 6 dB in this case, which from what I discussed earlier in topic 2, that 6 dB would mean if you lost it, your range would be shortened by about half, or it's just effectively you've 6 dB loss where you don't really need it if you select the right antenna. If you look at the body wave antenna on metal versus a chip antenna, the chip antenna, when you place it near metal, does become more directive. In this case, the peak gain's about the same, but you can see that the body wave is more omnidirectional. It's not, it will give you better coverage. If you mounted that, say, on the top of a machine, you get more omnidirectional coverage in the XY plane, and you would achieve a monopole-like pattern, but with a much more physically low-profile, robust solution. So in summary, when we look at the performance of body wave versus conventional antennas, like I looked at from commercial antennas off the shelf, and we look across the frequency band, this graph shows that in the bluey purple bar, that is the average performance difference we'd expect by replacing a printed antenna or chip antenna with body wave on a difficult platform in the worst case scenario, non-line of sight. And then the green arrow bars are largely there for, it depends what we're comparing it to, whether it's a chip antenna, whether it's an optimized PIFA antenna on that board. So we're within, at the frequencies that we're interested in, you're looking at about between 10 and 20 dB performance gains that we've validated in that non-line of sight by getting a repeatable impedance match, optimizing the radiation efficiency, controlling the launch of the electromagnetic waves for the propagation, and those three things combined give us the performance gain on difficult platforms. What does good look like for some of the people that we work with? Some look for 3 dB in the performance gain, and what we try and target is definitely over the 6 dB regardless of the frequency you're looking at. So over 6 dB, which would double the distance or half the power. Thank you for listening, and I'm happy to take any questions.
Thank you, Gareth. That was a very comprehensive introduction to the challenges of designing wireless wearable solutions, and excellent presentation on how to overcome those. Just going to some of the questions. We've got one here. I'd be interested if you've tested body wave receiving GNSS signals, i.e. L1, L5 bands.
So we haven't at present developed the antenna down at the GNSS bands, but we've done antenna technology either side of it, lower than a gigahertz and in around about 1.9. So I think most of them bands are about around 1.5 to 1 gigahertz. If there's an application there's no reason why we can't tweak the antennas to look at it in the future. Okay,
thank you. Another one, from your experience, which platforms are more difficult?
I would have to say I've spent my life looking at wearable communications. It's definitely the human body, and when you put the antenna close to the human body, and certainly as you move up in frequency, and you when I say close, I mean much smaller than a quarter wavelength from the human body. That's when I see a lot of problems, because with the human body you can mount it on any limb. It could potentially go anywhere on the human body, where metal's metal, and if you get the distance the same on metal, you're going to get largely the same performance, albeit whether it's good or bad. But on the human body, you could have different performance on every location you put it on, if you don't select the right antenna and get the wireless correct and optimize it. You can be confident that you could deploy it on the population.
Okay, thank you. Another one. I have a project where the Bluetooth antenna is inside an aluminium enclosure. It is close to metal for sure. What's your advice on that particular challenge?
Number one advice is get it out of the aluminium case. If you put RF in a can, you're going to have problems. Um, the the solution to this is probably not, if you're going to keep it inside some sort of, like I see a lot of medical equipment and stuff in a titanium case, and it needs to be sealed for that reason. You're going to have a lot of problems. Body wave wouldn't be your solution to that. Cutting apertures in the metal would be, but we've had where we were looking at some industrial equipment where you could cut an aperture in the top and embed the antenna just below that aperture. We were seeing good performance on metal. So what I'm saying is the antenna will sit below the chassis. It'd be flush. You could put epoxy at the top to fill the hole, but I never recommend putting antennas inside a sealed metal case. You're going to have to make the case your antenna and cut some apertures in it.
Thank you. Another one. Do you have broadband antennas suitable for LTE-M?
At present, no. The body wave antenna that we have within AntennaWare is a narrowband solution. Now, as we can get a bit broadband, obviously, when you go up in frequency, we can cover multiple UWB bands with our solution. But down at the LTE bands, there's a lot of different frequencies you have to cover. We could cover some of them, but at the present, we could not cover all of them with our current solution. But it's a good question.
Yeah. And another one. Printed and chip antennas that I have used need specific ground plane shapes and keep out areas. Do you need the same for the body wave antennas?
So that's a good question. So yes, printed antennas, chip antennas tend to, in general, require a cutout on the ground plane. So we call that the keep out area. The body wave antenna sits on top of a ground plane, and that largely explains why we get the isolation from the human body and why we can put it close to metal, within like a millimeter off metal. So the answer is no, we don't have a keep out area, and it sits on top of the ground plane. It has a footprint, obviously, we have to feed the antenna, but it sits above the ground plane layer, so there's no real cutout area. We do like a clearance of a couple of millimeters around the antenna, but there's no reason why you can't populate the back of the PCB with circuitry around the antenna with matching type circuitry or small components, or even place the antenna above a battery.
Great. That's it. Thank you, Gareth. And thank you everyone who's attended the seminar. Within the next 48 hours, you'll receive a follow-up email with a link to the recording of the webinar. If you'd like to continue the conversation and discuss a specific project that you have in mind, then please contact me, Gordon Petrie. There's the email address down there. It's gordon@antennaware.co.uk, or reply within the email that is going out with the webinar. There's one question that's just come in, so I'll ask Gareth to answer. Do you have a minimum ground plane size recommendation?
No, like I said, around the peripheral antenna, we'd like a couple of millimeters, if possible, so we can optimize it. The antenna won't change. We can optimize it for smaller ground planes. We've, like in some of the pictures that I showed in this webinar, we had it on very, very small ground planes, like a USB dongle. So like a couple of millimeters around the antenna, depending on what frequency you're working at, depending on what antenna. Obviously, larger ground planes give you a bit more isolation, but we've had excellent performance on minimal ground planes, so a couple of millimeters around the edge of the antenna.
Lovely. Thank you very much. And thank you again, everyone. As I said, we'll be sending out the webinar link in the next couple of days and look forward to any inquiries that you have going forward. So thanks again. Bye.